Good morning and welcome to another MEscope webinar. My name is Mark Richardson, the marketing director here at Vibrant. And I am joined by Brian Schwartz, Director of Engineering, and also Mark Richardson Sr., my father, who is the founder and CEO of Vibrant. And we have a good webinar for you today. We are talking all things modal analysis and curve fitting, and we're going to talk a little bit about ODS. There is a lot of content to get to. So we're probably going to break this webinar up into 2, maybe even 3 webinars because there's just that much content to get to. And we want to make sure that we cover it all. Traditionally, when we cover this, back in the day when we were doing modal courses, this would be a 3, sometimes even a 4-day course. So we're going to try and compress a lot of this into 2 or 3 webinars. And as always, we want to allow time for questions. So during the webinar, everybody's going to be on mute. And if you have questions, feel free to type those questions in the GoToWebinar dialog box there on the right-hand side of your screen. And we should be able to get to those questions at the tail end of the webinar today. What else? Let me think if we have any other items to talk about. We will talk a little bit about pricing. We have some new offerings as well for a hammer kit and some MEscope software bundles. So we'll talk a little bit about that. We want to introduce some of that, which is very relevant to the webinar today. And with that, let me just hand things over. We'll get going because we got a lot to talk about. Dad, you want to take it over?
All right.
Here?
Thank you, Mark. Hopefully you can all see the PowerPoint slides that I'm going to start with today. Then I'm going to go into using MEscope, and we're going to do some ODS animation because that's really where curve fitting starts. And we'll talk a little bit about the difference between an ODS, an operating deflection shape, and a mode shape, and how resonant vibration is really what vibration is all about. Once we understand resonant vibration in terms of modal parameters, mode shapes, frequency, damping, and how they participate in what we actually measure in the real world, which is an ODS. So let's go ahead and get started. And these are some slides, as Mark mentioned, kind of an introduction to modal analysis. So I'm going to go very quickly through this, and we can come back. I've got the thumbnail over here on the left-hand side, so when we get to the questions and answers, don't be shy. If we skipped over something very quickly, we can go back and review it, because understanding curve fitting, that's a means to an end. That's a way to extract modal parameters from vibration data. But the whole idea behind modal analysis, and the reason that we have customers worldwide using MEscope every day in their job, is to understand resonant vibration and to understand how structures behave when they get excited with dynamic forces. So here's a slide that says, why is modal analysis needed? Some of the reasons, if we're working on cars or airplanes or anything that people ride in, uncomfortable, vibrates too much, too difficult to control. Again, airplanes, rocket ships, whatever, too difficult. Makes too much noise. Any kind of machinery in a factory or in a neighborhood, or now these wind turbines that are showing up everywhere. Not only are they noisy, but they make people sick because of the vibration that they create. Doesn't maintain tolerances, wears out too fast, and breaks unexpectedly. These are problems that certainly in any kind of a plant, process plant, refinery, chemical plant, every plant in the world has what we call machinery monitoring programs to monitor using vibration. Here's the next slide. It says laws of modal analysis. Now, these are the laws that I've made up after being in this business for so many years. Of course, you know, a law is something that we can observe that doesn't change. Gravity doesn't change. That's why it's called the law of gravity. These are 4 laws that I've observed over the years, and I think anyone who works with vibration, machinery maintenance, what's called test and measurements, getting shakes and rattles out of car bodies and so forth, would understand this and agree with it. Anything with mass and elasticity will resonate. So the vibrant logo down here, the mass on the spring with a damper, this has been our logo since we started, that will vibrate. However, it's got to have forces applied to it in order to vibrate. Now, I could just push on the mass. Let's say I have a mass on a spring with a damper and I push on it with a static force and then I release the force. That mass will vibrate on the spring for a while. Now the damper is going to damp out the vibration. So we got to have some forces applied somewhere. You could interpret that as an initial condition, and the mass on the spring wants to return to its undeformed position. All modes are excited at all frequencies. Now that's something that people don't understand unless you've been working with vibration data, but we will certainly use that when we do curve fitting. And even more so, all vibration is a summation of mode shapes. So that is another underlying principle, underlying law that we use in modal analysis, and especially when we do curve fitting. This is another way to look at vibration. We need forces to cause vibration, but if we remove the forces, as I just mentioned, the mass on the spring, the machine, the structure will continue to vibrate, at least for a while. Now out in space, where there was no damping to damp out the vibration, there have been failures of some of our space vehicles. Back in the Apollo program, antennas would be forced into vibration, and then even when the forces are removed, the vibration would continue without any way to damp it out, and things would eventually fail. So when we talk about forced and resonant, all vibration is a combination. We need forces to start the vibration of something, and then even if we remove the forces, resonant vibration will continue, at least for a while, until the damping damps it out. So when we talk about forced vibration, we're really talking about, and then we're talking about operating deflection shapes, operational deflection shapes. We use the term operational modal analysis. That's where we can't measure the forces. Now, when we talk about curve fitting, we're going to get into the most common way of curve fitting, and that is with a set of FRFs, or frequency response functions. So I'm getting ahead of myself here, but we want to keep in mind that there are 2 different types of shapes: operating deflection shapes and mode shapes. Mode shapes are associated with resonant vibration. I like this way of explaining resonant vibration. It's called the trapped energy principle. And when forces are applied to a structure, they impart energy to that structure, and it gets trapped within the boundaries, moves freely within the boundaries, cannot readily escape. So striking a bell causes it to resonate. We're all familiar with that. The material is deformed by the little ball or whatever is inside the bell to cause it to vibrate, and then eventually it stops vibrating. And again, the damping mechanism, the most common one, is the surrounding air. So the bell is pushing the air around, and the air absorbs the energy, and eventually it stops vibrating. Now, if I strike a sandbag with a hammer or an impactor, it won't really resonate because the energy doesn't readily travel between the molecules of the material that it's made out of. So not all things will resonate, but a lot of things will. Here in California, we're all very familiar with earthquakes. I have actually witnessed the mode shapes of the ground when an earthquake occurs. I was in my car back in the Loma Prieta earthquake, and I could actually see the surface of the earth deforming due to the earthquake. So that was resonant vibration, but again, it damps out very quickly. What is an ODS, or an operating deflection shape? It's forced motion of two or more points and directions, and we call those DOFs. So a shape is motion at each point relative to all others. So as soon as I've made two measurements on the surface of a structure, and now we're doing it with video cameras and high-speed videos also, we won't get into that, but we've had webinars where we can extract vibration from a video just like we can extract it from two or more accelerometer measurements. So motion is a vector. It has location and direction associated with it. Keep that in mind, and we call that a degree of freedom, or a DOF. So that's the way we identify motion in either an ODS or a mode shape, by its DOFs. So what is modal analysis? Here's a quick definition. It's a process of characterizing the dynamics of a machine or structure in terms of its modes of vibration. So what do we mean by a mode? Well, there's really three different ways to define the mode numerically, and we'll get into that when we get into curve fitting. So a mode is another word for a resonance. And each resonance in a structure has what we call a natural frequency, or a modal frequency. It has damping associated with it. So there's many different damping mechanisms that we could identify, but the most common one is the surrounding air. So most things, at least here on Earth, behave like a speaker. They push the air around when they vibrate. And that's how the energy gets absorbed eventually out of the vibrating machine or structure. Or if the forces are continually applied, then it continually pushes the air around and we either hear it, or if the forces are removed, then the air will absorb the energy. So that's what we call modal damping. And then the mode shape is the spatial definition of what we call a standing wave motion. So what do we mean by that? Well, resonant vibration has this is the whole purpose of MEscope, that we can actually see in slow motion with some animation the mode shapes of a structure after we've done curve fitting, or we're going to look at just ODS data, and we'll see that for a lightly damped structure and light modal coupling, what we call coupling, we'll look at that in a minute, then the ODS is actually dominated by a mode shape at one of these natural frequencies. So standing wave deformation, we animate it with sinusoidal modulation or amplification, and we call that a mode shape. Okay, here's another way to think about one of the laws of modal analysis. All vibration is a summation of resonance curves. So each mode is represented by its own resonance curve. Now this is an FRF here. You can see log magnitude of the FRF. That's what we actually measure, the magnitude and the phase of the FRF. We'll get into more of how that's done in curve fitting. But we assume, and it happens to be true in nature, that we can take these modal parameters and create in curve fitting. What the curve fitter does is actually creates a resonance curve for each mode, and the overall data is curve fit with a summation of contributions of these resonance curves. So that's intuitively a kind of a look at what curve fitting is all about. A few more properties of modes. If they get excited, they can be dangerous. And we know this in many different applications. We can think of a mode as a mechanical amplifier. And the mathematics, incidentally, and we'll get into more mathematics in our second part 2 of this series on curve fitting. The mathematics is identical to the way an amplifier, electronic amplifier, is defined by an electrical engineer. So as mechanical engineers, we're using very similar mathematics, and it's amazing to me that the real world actually behaves in a manner very similar to an electronic circuit with, that's made for amplifying music. So at or near a natural frequency of one of these modes, the energy in the structure can be readily absorbed, again, caused by applied forces, resulting in a high amplitude response. So we're talking about dynamics here, dynamic forces and exciting resonances. That's a little different than just putting a load on a structure, a static load, and maybe deforming it and fatiguing or breaking the material, exceeding the elastic limit of the material. Here, we apply a dynamic force, and these resonances show up as peaks in an FRF. This is a log magnitude of an FRF, frequency response function, where we can just look at an auto spectrum of a response, and it's going to have peaks in it also. So if we excite at or near one of these frequencies, and sometimes not even near the frequency, depending on how the force is applied, the resonance, the response due to the resonance getting excited can far exceed the static loading. Here's another property, that modes are sensitive indicators of physical changes. So this is a simple example here of a plate with a crack in it and 2 different FRFs, the magnitude again overlaid. And as you go up in frequency, the structure becomes more sensitive. Those higher frequency resonances become more sensitive to the crack, the failure in the material, and they're going to shift down in frequency. So this is a little bit of a crude picture here, but it's showing the before and after of an FRF, before the crack and then after the crack. So that's used as a way of, in the machinery maintenance area and plants. And we have software for that. We're not going to get into that today. That's a lot more advanced use of modal analysis. Here is a slide, and it shows the variety of measurements that can be made on a real structure to extract its modal properties. Now, sinusoidal excitation is the way modal has been done for going way back into the 40s and 50s with analog gear before the digital FFT and so forth, exciting modes one at a time with sinusoidal excitation. And again, as I've mentioned, what's measured is the ODS. And an ODS is response at 2 or more degrees of freedom on the surface of the structure. And just capturing that data with analog gear is a good approximation of a mode shape. And that's the way it was done in the bad old days. But in the 60s, with the creation of the fast Fourier transform, the FFT, and then in the early 70s, the onset of digital spectrum analyzers that use the Fourier transform. And now they're very common tools for engineering and vibration analysis. We can look at the Fourier spectrum. But in order to look at a mode shape, we need to capture all of the data simultaneously. and that's difficult to do. So we'll talk more about that as we get into this. And we don't generally, with impact testing, or even shaker testing, if we don't have enough accelerometers to put on the surface, it's not a simultaneous acquisition. Now with the video camera, it is. The video camera is actually simultaneously acquiring the motion of the surface. So that is another way to capture the motion, and then with the Fourier, with the FFT, look at the Fourier spectra. Auto spectra, a little more of a processing, but again, Fourier spectra, auto spectra are going to have peaks in them at a resonance. Now we can show the relative amplitude by, and we can actually do this in MEscope to curve fit auto spectra, which we can grab with a single channel analyzer. However, there's no phase. It's just the magnitude. So over here are the common ways to acquire data with at least a 2-channel analyzer. And Mark had mentioned we've got a new impact testing kit on our price list that starts with a 2-channel analyzer. That's all you need is a impact hammer and a uni-ax accelerometer. And now you can make FRF measurements, you can make transmissibilities, cross spectra, and ODS FRFs. So these are other types of measurements you can make, transmissibilities, cross spectra, ODS FRFs, where you can't measure the force. So this is more for operating data and doing an operational modal analysis. FRFs, we have to measure the force spectrum. So we're going to talk about curve fitting mainly of FRFs in this series, but maybe in a part 3, we'll get into curve fitting some of this other data. Let's move on. Modal tests start to finish. So here's, if we're going to test something with accelerometers and an impactor or a shaker, we want to mount the structure with desired boundary conditions. So if we really want to see things moving around well, typically we do it with soft mountings, bungee cords, foam rubber, and that's what we would call free boundary conditions. In other words, it's free to vibrate. Once we start attaching the structure to the floor or the wall or other structures, the mode shapes and the ODS will change. But we want to let's just assume we're going to do a free test where we got soft mounts, and the examples I'm going to show you here in a minute are the data was taken that way. Lay out the test points. So again, we're going to discretize the surface with a number of points, and when we attach the sensors, the direction of the sensors. So if we really want to see 3D motion, we want to use a triaxial accelerometer, which will sense motion in 3 dimensions. Or if we're just looking at dominant motion in one direction, a uniaxial will be fine. And then an analyzer or a data acquisition system. Now, MEscope works, we have what we call an acquisition window, which is part of MEscope, that will extract time records from a number of different third-party data acquisition systems. And then MEscope will do the FFT and the signal processing and the windowing and all those other things that is typically done in an FFT analyzer, a spectrum analyzer, to make the FRF measurements. So now we want to start making FRF measurements. And again, if we want to look at a mode shape or an ODS, we got to have at least 2 or more DOFs, points and directions, on the structure where we acquire data. Now, what is this at least one row or column of the FRF matrix all about? Well, we're going to get into that in part 2. I'll talk about it a little bit today, but it's more mathematics, and this is where modal can sometimes go right over the head of many engineers and dynamicists who are not familiar with the mathematics. We're going to get into a little bit of it today because we need it for curve fitting, but we'll come back to it in part 2. Okay, if we're going to do modal and MEscope, we need a 3D model so that we can look at the spatial definition of the structure, the deformation. So if it's just the FRF data itself, we put a cursor on the peaks of the data, we can see the ODS of the structure at various frequencies. We need a model to do that. So we've got a bunch of drawing tools in MEscope, or we can import them from a solid modeling package or FEA. And the ones we're going to use today are what we call photo models. So they were actually built with a program called Photo Modeler, where you take a number of still photos of the test article and then create a 3D model in that software, which we can then import into MEscope and use for looking at our data. MEscope can either import the data, the UFF, Universal File Format, is the most common file format that's used by many analyzer manufacturers, and it's been common in the industry since the 1970s. So that's, and it's it can be either ASCII or binary, or as I mentioned, MEscope has an acquisition window that will attach directly to the hardware. The most common is through the USB port. And so many of the data acquisition hardware manufacturers allow you to talk to their hardware directly. So we've got that built into MEscope for a number of different front ends. First thing we want to do is animate the operating deflection shape. So we want to see if the structure is moving around and is deforming with something that looks like a mode shape. And for lightly damped and lightly coupled structures where the modes are separated by the natural frequencies, separated by different frequencies, the ODSs will look like a mode shape. Then we get into actually estimating the modal parameters by curve fitting. So we're going to get there today, I promise. What are the parameters? Modal frequency, modal damping, and mode shape. And then we want to animate those mode shapes. And then we'll actually do some comparison with the ODS data, the raw data right off of the FRFs, and compare the two. And we'll talk a little bit, hopefully before we get to the end of the webinar today, how we numerically compare ODS data with mode shapes. Okay, well, here's something I've already been talking about in a number of different ways, and that is experimental mode shapes are extracted from ODS measurements. So as soon as I make 2 or more measurements on the surface of the structure, now I've got, and then I can process them in MEscope to get their frequency domain, or I can work directly with the time domain data. So we have what's called a time domain ODS, or time-based ODS, or a frequency-based ODS. And we can do curve fitting in the time domain of the impulse responses. And we'll do that. We have a curve fitter that does that in MEscope. Or we can curve fit all these other frequency domain types of measurements with frequency domain curve fitting. So we're going to do that today. But FRFs will be the most common one. Fourier spectra, if we again have to simultaneously acquire all the data, which is if we're going to put accelerometers on the surface, it's going to be expensive and time consuming to wire it all up. Cross spectra, again, there we're using one of the responses as a reference. If we're going to go back and measure FRFs, where we actually measure the cross spectrum between the force and the response, then we can make them one at a time. Cross spectra, we can make those on a machine that's running, or a car that's on a test track, or an airplane flying around. We can't measure the force. Now, we make some assumptions there, but again, we can get modal data, mode shapes and so forth from that kind of data. And then ODS FRF's the same thing. That's something special to MEscope, where again, we do signal processing on our time responses to reduce noise and do spectrum averaging to do that, and windowing if it's random data. And then again, we can do curve fitting on that kind of data. So let's move on here. Let me see where we are. Well, now I'm going to talk about different ways of measuring FRFs. Let's go to MEscope right now and just look at some. I'm going to put this down. We'll come back to this, and let's. I've got MEscope right here, and what I'm going to use. This is our opening window. This is called the start page, but I can get that up here from, you can see from the help menu. And we've got a number of other things to do with the licensing, and but I'm going to come down here to these demos, and we've just changed them recently. So when you install MEscope, you will install a number of modal demos. So they involve curve fitting, and you can see we got some different models here, a Corvette, a flat plate, a gearbox housing. This is called the Jim Beam, a model airplane, and the Vibrant Beam. So we're going to go through and look at some of these. And then if we go to ODS, we've got some of the same models, but we're going to use hotkeys. Now, you're probably not familiar. Hotkeys are a standard feature in MEscope, and it's another programming language that's very high level. All it is a spreadsheet of MEscope commands, and the hotkey associated with each spreadsheet allows me to execute the spreadsheet in MEscope and carry out a series of commands. And we can put loops and if statements and other things into it, but I'll show you some of those. But I'm going to use the hotkeys today to demonstrate. We'll start off here with ODS and then use the scripting to do things automatically. And then the last section here is video ODS, and we only got one example here, and we're going to be adding some more as we come up with different examples of ODS data, extracting ODS data from a video, from frames of a video. Let's go back here and just start one. I'm going to take the flat plate and just double click on that. And this is a special command to me because of my software that allows me to make changes to these demos. In your version, if you own an MEscope license, I might mention also that we now have monthly subscriptions on our website of many of the MEscope packages. We won't get into packages, but there's a number of them. ODS and modal are the most common ones. Now what you can see here, I've opened up this project called Flat Plate Modal Demo, and you can see these are hotkeys. So I'm using ribbons I prefer ribbons. Microsoft has switched many of their applications over to ribbons. If you don't like ribbons and you just want to use a menu structure, we got two different menu structures. Let me show you real quickly where that is under MEscope options. Menu style. So see, I've got ribbons displayed, but I can go with a single menu, and there it will put a menu bar up at the top of the screen with the commands for the active window. So I need to click around on various windows in MEscope to get a menu of those commands. And then I can also display a menu in each window. So this is an older Microsoft way of doing things. Originally Windows, that was the only way you could display a window, was with a command, a menu of its commands. But anyway, they've moved more to ribbons now, and so I prefer to use ribbons also. So I'm just gonna close this, and so here's a ribbon with hotkeys on it. And you can see there's a number of curve fitting methods here. Quick fit, that's the one we're going to look at today. That's our quick, and we'll call it dirty, but it's very versatile way of doing curve fitting on FRF data. We can do it on cross spectra and ODS FRFs, and even a set of auto spectra if they're taken correctly. And then we talked in our previous webinar about rapid testing. So we'll come back to that. Maybe in part 3, we'll talk about how to take data with an impact hammer and an accelerometer in a rapid test, and then do quick fitting of that data and look at the mode shapes. These other 3 fitters are what we call AF polynomial, complex exponential, and Z polynomial. And those are 3 curve fitters that are in our Modal Pro package. And that's what we call our advanced modal analysis package. We're just going to look at quick fit today because that's the one that's in our basic modal, what we call visual modal package. And then next time we'll go in and use those other curve fitters and compare results. You can see over here we're going to compare frequency and damping and mode shapes. So let's just go ahead and I'm going to click on this. And now that what it's doing is it's running a script. So it's running a program that I created in MEscope, and it just did a whole bunch of things. It finished the curve fit. And now what it's showing is the quick fit mode shape on the left. It's doing a comparison animation of 2 versions of the flat plate here. And it's cycling through the mode shapes. So up here, the mode shapes were stored in a shape table. So we use shape tables in MEscope to store both ODSs and mode shapes. And we can look at what's in there and more of the details, but the animation is comparing the mode shapes up above, and then on the right in our picture here, where the source of the data is the FRFs, and those are down here. And you can see that as I click along here in the mode shapes, the software actually finds the peak in the FRFs that is closest in frequency to the frequency of the mode shape. So as it cycles through here, I can quickly compare answers, basically. I'm comparing a mode shape from the curve fitter with the ODS at the frequency that's closest to in the FRFs to the frequency of the mode shape. Now you can see that if I zoom in here a little bit, the resolution, I've got 424 hertz here, and up here, well, now we've moved to 752, and up here, the curve fitter has given us essentially the same frequency with a little bit of change, and then a damping estimate. All the damping is expressed in two different ways. This is in hertz. Now damping, when we say it in hertz, that is the width of the resonance peak. So this resonance peak is, all these peaks are about 2 hertz wide. And the percent of critical is the more common way, where we divide the damping in hertz by the frequency in hertz. That's a rough approximation. It's actually a square root of the sum of the squares of the damping and frequency, but it's percent of critical is what many people prefer to use as a measure of damping. And we'll get into that again in part 2 when we look at the equations that are used for curve fitting and look at that in more detail with the mathematics. Let me go back and just press this again, and we'll just do it over again. So here it is in the curve fitter doing some curve fitting, and so it's rattled through a whole bunch of steps here. Let me just show you what it did when I press this button. I'm going to hold down the control key, and here is the script. Here's the program that it actually did. And it's very simple in MEscope. You give it a window name, you give it a command, and then you tell it whether to open a dialog box or not. If the command requires some input from a dialog box, you can see in this case, none of them needed an opening of a dialog. And then here's a little description of the command. But here's what it did very quickly. First, it centered the data block. Then it opened the curve fitting. Then it deleted all of the curve fit data that might have been associated with that data block. So the curve fit data is stored with the block of FRFs in this case. So when I come back to MEscope tomorrow, I can open it up and open up curve fitting, and it will show me all the data. But here it's deleting it. Now, mode indicator count peaks, we'll look at that in a minute. That's the first step of curve fitting. There's actually 3 steps to our quick fit. The first step is to process the data and draw up a peaks function, what we call a peaks function or a mode indicator. Now this is in this script. You can see that the window is this script. It puts it to sleep for 3 seconds. So that just causes a pause here in the execution. Then it does the quick fit. So we could change this. We could even change this to maybe, I don't know, let's just make it, we'll double it to 6 seconds. So now when I hit this hotkey up here, it's going to sleep the script for 6. Oh, it didn't save it. Let me put it in again and say enter. Okay, so it should save it now. Okay. So after it's done the quick fit, then it saves the shapes. That's another step in curve fitting. And then it closes the curve fitting. Now it goes to the quick fit mode shapes that got saved. You can see they got saved here in a shape table called quick fit mode shapes. And that happened here. And then the animation started. And we're doing a sweep animation through the source data. And in this case, it's the quick fit mode shapes. So that's what we saw happen. And then there's some other commands down here that position all the windows so we can see them. And then finally, this dialog that came up. So let's just go back and press that again, and it's going to do everything very quickly. So you can see it's sleeping for 5 seconds, and it went through curve fitting, and now it's sleeping again, and now it started the animations. So it executed all those commands in the script window. And then it ended by putting this up, and you can see the dialog's got a little timer associated with it, and I can set that up. And after the timer expires, it takes that window down. So let's go back. And now I'm going to go back and let's just open up the data block itself. Well, here it is. It's down here. First I want to stop the animation. So animation. Okay, we're in the animate a pair, so I need to animate, stop that. Here's my data over here. Let's center the window. Let's go into curve fitting. So that was a command down here, open curve fitting. So here it is. This is the curve fitter. And you can see that up above is a log magnitude of my FRFs. So here you can see a spreadsheet of all the properties. There was 30 FRFs in there. Those were the 30 points on the flat plate. And the response was taken with an accelerometer. So the units are G's per pound. This was done with an impact hammer. And so these are the two important things for the FRFs that you need to label when you're taking data in a modal test. The degrees of freedom. The first degree of freedom, you can see there's a colon here. The first degree of freedom is the what we call the roving sensor. In this case, it's the accelerometer that was moved around to each of the points. No, it was a roving impact. So correction, let's go back. The way the data was actually taken on the flat plate was a roving impact. So it was impacted at each of the points in the Z direction. So let me put this back here. So it was roving impact, and the accelerometer was attached at 0.1 in the Z. Well, where is that? That's over here in one of the corners. Display, show points, point label. So, okay, so here it was attached over here at 0.1, and then it was a roving impact. Very simple modal test, probably the easiest one to do on any structure. So this is our data, and let's just clear out everything and do it all over again. So I'm going to delete all the fit data because that's what the script was doing. And there we are. Now over here, you can see we got a mode indicator, frequency and damping, residues, and save shapes. So there's actually 3 steps to curve fitting here. First step is what we call a modal peaks function. And we got some other types of mode indicators here, but let's just use the modal peaks function and count some peaks. Now it says, what part of the data do you want to use? The real part, the imaginary part, or the imaginary, or the magnitude? Typically in an FRF, the imaginary peaks are the sharpest. And so we're trying to locate the modes and count the number of peaks. So there, I went ahead and said, okay, and so this mode indicator is a modal peaks function, MPF, using the imaginary part. And you can see it's with a log magnitude here. So this is for decades. And so these peaks are sitting up nice and high, and we counted 5 peaks. So the software said, hey, there's 5 peaks in here. So that's what we need to get this curve fitter started, is to tell it how many modes. And all curve fitters are like that. Now, when we get into the more advanced curve fitting, rather than tell it how many modes, we'll let the curve fitter figure out with what we call a stability diagram how many modes are actually in there. And the curve fitter will fit with 1 mode, 2 modes, 3 modes, all the way up to, we can go to as many as we want, 50 modes. And then the software will clean up the stability diagram and show us where what we call a stable pole or a stable mode is, where its frequency and damping is the same with each of the curve fitting models. So we'll get into that next time. This curve fitter is much easier to use because if the mode indicator won't show me how many peaks, then I can simply go in here with a with a band cursor and set it up around one of these peaks here and say, curve fit that data for me. So we'll go back and try that in a minute. All right, we're in a polynomial and it's called single reference global polynomial. Well, we got local polynomial, we got multi-reference polynomial. So these are different forms of this quick fit. And we're just going to go with the single reference. So what we're going to estimate here for these 5 modes is the frequency and the damping. So we'll go ahead and do that. Let's put up a little dialog here. Do you want to continue? It's going to find 5 modes and the frequency range. I don't have a band cursor up. Extra polynomial terms. You see this up here, extra polynomial terms. This is using something we call a rational fraction polynomial form of the FRF. So now we need to get into mathematics, and we might go back here in a little bit. We're running out of time today, so we're going to save that for part 2. We'll talk about those extra terms and where they came from and why we need them. But let me just say they are in here to curve fit away the residual effects of out-of-band modes. Now, do we have any out-of-band modes here? Yeah, we do. If I scroll through, you can see that this curve here, this magnitude, is indicating that there's something else at a higher frequency that got excited by the impact hammer. And here you can see it again. The magnitude is growing, so there's something beyond our analysis frequency range that got excited by the impact hammer. And that's why we need those extra terms in there to curve fit away. We actually throw away those extra terms after we have done the curve fitting. So what happened here when we press the frequency and damping button is, I'll do it again because you probably didn't notice, but we got the frequency and the damping both in hertz and in percent critical of those 5 modes. I'll do it again, and it's just going to add 5 more estimates of the modes. I can delete them and go back and curve fit, delete. Well, we can delete all the fit data. Do you want to do that? So let's just go back and go back to the mode indicator and put the mode indicator up, go to the frequency and damping and compute that. Okay, so there we are. The final step, there's 2 things here. We're going to do a second curve fitting step. And I didn't get into all the benefits of that. We'll cover some of those slides perhaps next time, because I think we should probably end this, Mark. And let me just go through quickly, and I'm going to do the residues. This is a second curve fitting step, and bingo, it's just as fast as, that's why we call it a quick fit. And if I scroll through here, you can see the magnitudes of the fit function is now laying on top of the magnitudes. And if I scroll down here, I can actually change over and go to, what do I want to do here? Well, let me just move on. And the final step is to save the shapes, and we can put them in here to the quick fit, and we'll do a replace. So that would finish everything, and then I could just go and animate them, because here is the table with my results in it, and I could just go start the animation, and you can see this is my animation source. So now I'm looking at those mode shapes. Let's go, before I'm going to go through, and let's just try the Jim beam. And again, we'll just press the hotkey, and it'll very quickly go through everything that we've covered with the flat plate. And again, these are built into your MEscope now, so you can review this anytime you want to. It says press the hotkeys in order. So I'm going to come up here and press the quick fit hotkey. So here's the FRS for the Jim Beam. You can see there's 10 modes in here that the indicator has found. And bingo, it's animating the mode shape on the left and the ODS on the right. I can click on any mode shape that I want here, and it's going to find it's going to put the line cursor and show me the ODS, and then the MAC value between the ODS and the mode shape. So more things to talk about next time. Let me just go do the Vibrant Beam. And there's a lot of other things to show you here, but we're just running out of time. So I really want to save some time for questions. And we'll look forward to the next session, part 2. Now this, see, is a MMIF, is a different mode indicator, and there are nice sharp peaks here. And now we're seeing the same thing. We're seeing the mode shapes on the left and the ODS that matches the frequency of the mode shape. I can click here on any mode shape I want. Here's what I'd call first torsion, the lowest frequency. I got some other commands up here like surface only. I can just look at, I can take off the photo model, and this is reminding me that I can that it was attached to the surface. So this is a photo model that we made of the Vibrant Beam, and sometimes it's just easier to look at your mode shapes and your ODS data with a with a surface model. And I can rotate the model. Again, this is the script is doing this for me automatically, and if I click again, it's going to tell me you can do this anytime you want by just using the right mouse button. So that pretty much does it for me, Mark. Do we have any questions?
We do. If you have any questions, go ahead and type those into the box there and we'll get those answered for you. First question from Vinkata. I've come across several times negative damping value. What does it mean? Is curve fitting not properly done? So this question is about negative damping value.
Negative damping, yes. I mean, negative damping means that if I were to hit the structure with a hammer, if the mode really had negative damping, it would explode. The damping would be the inverse of damping out the frequency. It would amplify the animation. So negative damping, yes, is an indication of an error in curve fitting. Now the curve fitters, the advanced curve fitters, I think, will not allow negative damping, and we'll look at that next time because we use a stability diagram, and the damping values all have to be within certain tolerances, and I think they also have to be positive damping. So yeah, in the real world, any damping that a mode would have associated with it should be positive damping. Now, we'll look at impulse responses next time, and what that means is it's really a negative value, but we call it positive modal damping because the damping has to do with the envelope of the response of each mode, and that, if we look at the mathematics, it's actually a negative number because the envelope is damping down the vibration as we increase in time of the impulse response. So I'm throwing out a lot of words here. But the quick answer is no, the curve fitter shouldn't be giving you negative damping. It should be positive.
Okay, next question. For quick fit to work properly, is there any limitation on modal density and coherence of measurements?
Oh, well, that question is a two-part question. The questioner is asking about coherence. We haven't gotten into coherence. We discussed that a little bit, and we showed that in our previous 2 webinars where we talked about rapid impact and what's called transmissibility chain testing. More buzzwords. What are you talking about? Well, these are rapid ways of acquiring data, either with transmissibilities, with a chain of transmissibilities, or with an impact hammer. And we don't measure one row or column of the FRF matrix, so we can move. We don't need long wires. So that's something we covered before. We'll come back to that. And we showed coherence. So you normally want good coherence between your force and your response, or if you're using a reference, between your reference and your response signal. But you do the best you can. In the real world, sometimes things are very noisy, other things are running in the background, the floor is shaking, whatever. Coherence may not be perfect all the time. The best coherence you can get, if we go back to some of the slides that I had up here, let me go back. Where were we? Make the best measurements you can make. Modal test start to finish. You know, it all starts with good data. Curve fitting is not going to recover when you have bad data. The other part of the question was, can I use quick fit? Yeah, I didn't show you some of the benefits of quick fit, but let me just show you. Put this back down again. Let's just go back here to, let's get the flat plate. It's real simple. That way it won't be confusing. I can do quick fitting on this data also, but let me just open up the FRFs, and you're going to have to use your imagination a little bit here. Why didn't we open? Well, we'll get them this way. So the quick fit here is fitting over the whole frequency band, and it's getting all of the, you know, the 5 mode shapes there. But if let me stop this and animate a pair, we're going to stop the animation and set this up, and let's go into curve fitting and delete everything. We start over. Okay, you know, are you sure? So now I'm going to turn on the band cursor. So I can use quick fit like this. Now just imagine that I got some data and I got a nice clean mode here at this frequency, but maybe I got a whole bunch of garbage out here, a bunch of high frequency stuff that showed up in my measurements, and it's very common. Just a whole bunch of high frequency noise or stuff that I just couldn't get out with my analyzer or my signal processing. But I can, if I've got a nice clean peak here, and even if I got mass loading and the peak is moving around, I can do a quick fit here. Let me just count the peaks. There's my resonance peak. Let me move these apart so you can see that. And then I can just go right in and do the frequency and damping, and I can do the residues, and bingo, I've got a nice mode shape. I'm gonna turn this off here. So there you can see I've got a nice fit. So, you know, the fit function should lay, the red function should lay on the data. Now this is just showing the magnitude. I should be able to show magnitude and phase. Why not? Move up, select cursor format.
Display.
There we go. Unwrap Bodhi. Oh, so here we are. This is good. we got a change in the phase here by 180 degrees, but you can see that it's matching the data very well. Let's go over here and do this one and see how it does. Phase is a little different. So we'll get into curve fitting next time, but let me go back and count peaks. So again, we can divide and conquer. That's the best way. And you know, other people say, well, you don't need a whole bunch of curve fitters. The advantage is when you got noisy data and you did the best you could, yeah, this phase is
Unwrap. You can't do unwrap phase with mode indicators because you've only got a local area.
Yeah. So let's just go back and look at the Bodie plot. So there we are. Yeah, we didn't unwrap. So now you can see that the curve fitter is right on top. Let me turn this off so it's not so confusing. So there I curve fit 2, and I got the modal frequencies down here and residues. Now, what do we mean by residue? We're going to get into that next time. That takes a little more mathematics, and here's modal participation. What do we mean by that? But this is a complete set of data for this measurement. Now, as I stroll through here, you'll see that the residues, frequency and damping are the same because we got what are called global estimates. So frequency and damping are global parameters. They should be the same for regardless of how I do the curve fitting. Now, we used a global fitter here, which went through and curve fit all 30 measurements and came up with one estimate of frequency and damping. Back here, you could see I had other fitters in here. I could use local, single reference local polynomial. So that's where it would individually fit each FRF. And if I had mass loading, that perhaps would give me a little bit better answers. And then the residue we get from once we have the frequency and damping, then we go through and curve fit to get the residues, which are basically the numerators. Any other questions?
Oh yeah, we got a load of questions.
Oh, well, let's get through them because we're already spent our whole hour.
Yeah, you got to stop going too far down in the weeds here.
All right.
All right, next question. When performing curve fitting, MEscope is looking for modes. How can I set the limit of the mode indicator function? This came to us from Randolph.
Yeah, well, let's go back here and start all over again and get things cleaned up. You see the mode indicator? There's what's called a noise threshold. And in the real world, you're gonna have lots of noise in your data. Let's go back here, open curve fitting. So you see this here, this little slider? The software is counting the peaks above the noise threshold. So that's very important when I work with noisy data. Now, in this case, I can put it all the way down here to the bottom, and it's still only counted 5 peaks. So it's going to show me where it's counted the peaks. Let me just go back and do that again. So there's the answer to the question. We better move on and get another question answered here.
Okay. Next question is from David. How well does the curve fitting algorithms work if the modes are closely coupled?
Yeah, well, let's go back and let's go to this case here. And that's what curve fitting is all about. Otherwise, we saw that even the ODS gave us a pretty good approximation of the mode shape. And we need to look at that carefully. And so I'm gonna go through and do the quick fit here on the Jim beam. So here's 2 closely coupled modes right here. You can see there's just a little bit of bump in the data. And those got curve fit simultaneously. Let me stop this and go back here and Now this is the imaginary peaks and they're overlaid. So let's clear that up so we can see what we're looking at here. And I'm going to go back and go magnitude. Okay, so now here's my FRFs, and you can see that there's two of them are very closely coupled here. Now the mode indicator, let's go into the open curve fitting. The mode indicator was able to actually count both of those modes because it goes through and looks at all the data. So you can see here when I get to some of these other FRFs, the lower frequency here, number 4, is showing up as a good peak. So this is why we need the mode indicator, because any one measurement, if I just counted peaks here in the first one, there's a little bump in the data, but there's no real strong indication that there's a second mode there. So as I scroll through here, and you can even see a little difference in the curve fit and the data here, because we're using a global estimate, which on the second step did a better job of curve fitting those peaks. Again, it's using all the data to curve fit the peaks. But to answer the question one more way, let's clear out everything and oh, I didn't do that right. Band cursor. I'm going to go over here in this area where we had the two modes. Now I can either count peaks here, and it will count 2 of them for me, or I can just manually go in here and say, you know, the mode indicator is not even, there's so much noise in this data and it only shows me 1 peak. You can see it says 1 peak over here. I can actually go in there and type in a 2. So I can say curve fit this data with 2 peaks, and let's just see what it does here. Okay, so it got the 2 modes and it drew up the vertical lines where it found the frequency and damping. And then if I go do the residues, so I can do this manually, and you know, it's going to get me some good results. Again, the proof of the pudding is in the animated picture, and maybe even a comparison with another curve fitter. So when we get to the advanced curve fitters, the other 3 that are in here, AF poly, complex exponential, Z poly, then we'll compare all of our answers, and we'll see that you know, even if I go along and curve fit my data like this, and maybe this is all noise out here, I don't care about it. Let's move on. Next question.
Okay, this one comes from Shivam. I think we may have touched on this. Is it wise to band cursor select each mode to estimate its damping, or is it fine to do it over the entire estimated MIF?
You know what I would do? I'd do them both and then compare answers. Save the mode shapes from both, and you can compare, you know, if we go over here and look at, compare this project was all set up with the mode shape tables from the quick fit, the complex exponential, the AF poly, the Z poly. It was saved as a project with all this in here. So I would do the same thing, go in and fit in small bands with the quick fit, and then fit a large band and compare the answers. The small bands should be better, but it's more work. So if I can just go in here and curve fit over the whole band, and especially with data like this, the quick fit can only handle up to 10 modes. Is that true? Yeah, let me go back here. I think it can only handle 10 modes at a time. So let's go back here to the Vibrant Beam, because it's got more than 10 modes in, I think. And if there's more than 10 modes, then yes, we have to go in bands with the quick fit. Oh, there's only 9 in here.
I believe the quick fit is also set up to automatically create bands.
Oh yeah, based on the mode indicator. But I can set the bands any way I like. Yeah, the quick fit is going to use the mode indicator and only use data around each of these resonance peaks. So that's why the mode indicator is important, because we don't want to be curve fitting over, you know, a whole bunch of noise. Let's go to the next question.
Couple more. This one comes from George. Do you get a difference in results between a fixed impact and roving impact modal test?
You shouldn't. You should get the same mode shapes. Modes are independent of the forcing function. They're only going to change if some of the material properties change, the mass stiffness, the damping, or the boundary conditions change. But you should be able to get the same mode shapes. And again, you could do both tests and compare mode shapes. Now, we didn't get into the whole business of how do we compare mode shapes in MEscope. Let me just show you the picture here very quickly, and we'll come back to that next time. There are some pictures in here somewhere that I want to show you. Hello, where are you? I don't see them. Well, oh, here they are. So here is a picture of what we call the modal assurance criterion, misspelled, so that'll get fixed because we'll use these slides again. But if two shapes lie along the same straight line, now this is we can only display it for a shape. One shape here has values of 1 and 1, and the other one has variable X and Y in it. So that's what's being plotted here. But you can see that if the two shapes are the same, and if we got them from a roving impact versus a roving accelerometer test, if we get the same mode shape, the MAC value will be 1. Now we have another indicator called a shape difference indicator. This is even a little more precise. There are only 2 places where the 2 shapes will give a SDI value of 1. Everywhere else, if the shapes are different, the value will drop down to some value less than 1. So we'll go into that again. These are numerical methods for comparing ODS data with mode shape data or mode shapes from 2 different curve fitting methods. So if we go back here and you know, we were showing the MAC values. Let me just run this again. We can do these. Once we have some scripts set up, you can just do it over and over again, which is really nice to go show those things. So here's the MAC value between the mode shape up here and the ODS down here. And you can see that, boy, there they are. They're right on the money, 100%. Some of these will be a little bit less. If I click around here, well, 99, 100%. So the ODS for lightly damped data is numerically it's different, but it's lying on the same straight line with the mode shape data. So MAC will tell us, are they the same shape? Do they lie on the same straight line? SDI will actually compare values and tell us whether 2 different curve fitters gave us exactly the same values. Let's go to the next question.
All right, last one here. Is it possible to make model checks like reciprocity or linearity check in MEscope?
Okay, certainly
you meant-
reciprocity.
Okay.
Reciprocity is something we don't measure for. We just assume it, but it's a good measurement to make. And let me just show you what you would use to do that. These are more advanced questions for sure. These are people who know how to use MEscope, which is probably most of you. But there's some commands in the data block under tools, and I'm looking for them. Data block correlation. So if I made a let's say I got an impact hammer and a uniaxial accelerometer. So I put the accelerometer at point A, I impact at point B, and then I switch and I impact at point B and I put the accelerometer or at point A and I put the accelerometer at point B and I measure those two FRFs. This data block correlation is the way to compare them. Now, if I compare the data with itself, the correlation, and this is using add to, no, we're gonna create a new file here. I'll just show you this real quick. Okay, so here I got MAC values and SDI values between the data block and itself. But if I had one FRF from impacted B, response at A, and then a second FRF impacted A, response at B, and then I did this correlation, we would see at every frequency whether they're the same or not. And that's reciprocity. That's the assumption we're making. And that's another word for that is symmetry, that the structure is symmetric. Go ahead, Mark. Read that question again, because there were 2 points to it, I think.
Is it possible to make model checks like reciprocity or linearity check in MEscope?
Oh, now linearity this is how you would check reciprocity if you made those measurements. Linearity, all of modal analysis is based on what's called linear dynamic motion. And that goes back to the differential equations, Newton's second law, F equals ma. That's a linear equation that involves force and acceleration. Now, does the real world behave linearly? Not always. So what we have to assume when we go out to do a modal test is that the real world is nonlinear, or let's just say not linear. Now, if we make these measurements, FRFs, those are linear measurements. I won't go into all the details, and then we curve fit them with a model for an FRF, an analytical model, which we call a rational fraction polynomial model, or an impulse response model. Those are both linear models. One of my slides, we showed superposition of the resonance curves. That is a linear concept. So does it work in the real world? Yeah, it works with real world data, but there can be cases where the structure is very nonlinear for whatever reason. And so what we're getting if we make FRF measurements and curve fit them and look at mode shapes is a linear approximation of what may be nonlinear or not linear in the real world. Next question.
That's it.
Oh, good.
Well,
those are all good questions. I appreciate all I mean, we ran over here. We're almost an hour and 20 minutes. So.
We're already in.
Come back next time. We'll announce it maybe in a couple of weeks, maybe in 3 weeks, 4 weeks, who knows. We'll fit it into our schedule and we'll go into part two,
yes.
More curve fitting. We'll use the stability diagram. We'll use 3 new curve fitters. We'll compare answers. But the quick fit, which is part of our modal package, is really a very versatile, and it has some real advantages. And I can kind of slice and dice. I can subdivide and divide and conquer, so to speak, my data and get some very usable results. With the advanced modal analysis option, we didn't really get into the price list and some of those different options, but there's two modal packages. One's called Visual Modal, the other's called Visual Modal Pro. So next time we'll show you the curve filters that are part of the Visual Modal Pro. Anything else, Mark?
That's it for questions. I did want to remind everybody, if you are looking for some hands-on modal training, I encourage you to go check out our partners at Navcom Engineering. They do an excellent 4-day hands-on modal analysis course out in Southern California. You can get more information at navcom.com, and or you can go out to our website at vibetech.com and click on the learning tab, and you'll find out all the information. There it is right there, 4-day hands-on modal testing and analysis. Jim does an excellent job, and he has taught many folks how to use MEscope and modal. With that, let's go ahead and wrap it up. We will get another webinar spun up here, like I said, a couple